In this last part of this lesson, we are going to look at how to extend the code we have developed so far to problems with non-zero Neumann boundary conditions. Okay. So for this setup, we are going to consider a different physics. Okay. So instead of the diffusion, we have heat transfer, conduction heat transfer. But although the physics is different, the equations are the same. Okay, the formulation is the same. The way we interpret the results in terms of physics would be different. So here our U becomes temperature. Okay, and instead of diffusion coefficient, we have conduction coefficient. Okay, now here I have a domain of size 10 by 5, and on the three sides, left to right and the bottom, there is a specified temperature of 20 degrees. On the top side, the top edge, there is an insulated boundary. This is the first setup, and in the second setup, on the top boundary, we have dou u by dou y as -5. Okay. Now, let us look at the expression for the force vector. We particularly focus on the contribution from the Neumann part. Now, here we have the integral. This is a line integral since we are in 2D domain and the boundaries are 1D objects. Okay. So, we have a line integral and we have n transpose h dl. Okay. So, dl corresponds to the line integral. H is the specified value of the Neumann boundary. Okay. This is like a normal flux. And then n is the basis function matrix. Okay. So, and we know from our PDE that h equal to mu nabla u dot n. Here n is the normal, outward normal. Nabla u is the gradient. So when we do the dot product, we have mu dou u by dou x nx plus dou u by dou y ny. Nx and ny are the components in the x and y directions of the normal n. Okay. So for the insulated boundary, h equal to 0. Okay. There is no transfer of flux. There is no heat flux, right? So h equal to 0. So when h equal to 0, Fe is 0. So we don't need to do anything. This is like a do nothing boundary in finite element method. So this is an advantage in finite element method. Whenever we have boundaries with the zero Neumann boundary conditions, we don't need to do anything. This is not like in finite difference method where we need to modify the kernel, the stencil, to incorporate the Neumann boundary condition. Okay, and when for the second case, when dou u by dou y equal to -5, again this is equal to h equal to -5. Why? Because on the top boundary, the nx is 0, ny is 1, so we have only dou u by dou y. And if you assume mu equal to 1, we have dou u by dou y equal to h. So h equal to -5. Okay, so that is how we interpret this Neumann boundary condition. Next, we see how to implement this in a finite element code. Okay, now if we look at this element, our 4-noded element, we can see that it has 4 edges. Okay, if you explore this element, we can see that it has 4 edges. Now, in order to integrate this boundary term, we need to perform the integral along one of these edges, one or more of these edges. If they are internal, we don't do anything, but if they are external, we need to perform the integration, okay, along the edges. Now, since this is a 2-noded element, we map it to 2-noded element in 1D. Okay, this is our local element that we used to solve the 1D PDE. Okay, the difference is that in the physical domain, the 2-noded element can have coordinates both x and y non-zero. Okay, we map that to 1D element with only one coordinate, right? Only xi. So there is some slight complexity that we need to deal with. the complexity is in creating the mapping and the Jacobian. But that is for a general case. For the particular case when h equal to constant, so we can take h outside and we can integrate in the basis functions, okay, in this domain. So then that gives us 1 over 2, 1 over 2 and over the multiplied by the length of the element h. Here h is the distance between the 2 points of the nodes. Okay, so these h2, h1, y1, y2, y1 are the x and y coordinates of the nodes in the physical domain. Okay, so if h is a constant, then we can simply use this expression to calculate the force contribution from the Neumann boundaries. Okay, if h is not a constant, then we use the Gauss points. Okay, we use the Gauss loop, and here inside the Gauss loop we need the Jacobian. The Jacobian is, like I said, it's not straightforward. Like, should we use dou x by dou xi or dou y by dou xi? Okay, we have to use both, right? So this is one direction, this is one direction. So we need to use the diagonal. Okay, so like this is like Pythagoras theorem. So we have dou x by dou xi, dou y by dou xi square under root, or we can also interpret this as the length of a parametric curve. Okay, so this is our j, and then with that Gauss point is the loop is the same. Okay, let us see how we can implement this. Okay, so most of the time the calculating the element stiffness matrix is easier, and calculating the element force vector due to the body force term is easier. Applying the boundary conditions is always difficult because we often do not have the information about the boundaries readily available. This is where the mesh generation software come really handy. Okay, if we generated the mesh on our own, then it would have been difficult to identify what the boundary edges are. Since we have used Gmesh, and with Gmesh we create tags, right? So this is our domain, 10 by 5 domain, and I have created two boundaries. So first boundary is for the left, bottom and right edges. Okay, and the second boundary is for the top edge, and then we have the domain. Okay, so in this way, when we export, we will have these stats. Okay, the boundary elements are tagged with the corresponding tags. Okay, so we can easily identify those. Now, so there are some modifications that we need to do. So in order to do those modifications, I'm going to create a file. I'm going to save this file, okay, as example 4. Okay, so we know that mu equal to 1, and for this case f equal to 5. Okay, so mu equal to 1, f equal to 5, and I have a mesh. I have this mesh exported. Okay, this mesh that we are using. Okay, for this example, this is the mesh we are using. Again, this is not a structured mesh. We have like unstructured mesh, but everywhere we have quadrilaterals. Let's check. Okay, so there are no triangles. Okay, I import this. Now, when it comes to the boundary conditions, okay, in this boundary conditions, when we calculate the boundary conditions, it is a constant value, so we really don't need, but we really don't need HC, YC values, but we can keep them. So everywhere on the left, bottom and right side boundaries, we have a specified temperature of 20 degrees. Okay, so this is the specified, but the important difference is that all the boundary nodes that we have calculated in the previous example, this array takes all the nodes on the boundary, including the one on the top boundary. We don't want that. We want bound nodes only on this three boundaries, so, which have a flag of or a tag of 5. Okay, so what we do, instead of starting all, okay, so I'm going to create a array, create an array, okay, empty array first, and then we loop over all the lines, okay, and then we check for the flag. Okay, if msh lines is the flag is stored as the third, okay, third column stored in the so okay, let me call this function. Okay, so clear all cnc, okay, we execute that. So here we have, so each entry has 3 columns, as you can see. And the third column, this is the flag. So all these edges with 5 correspond to the left, right, and bottom boundaries, and all the edges with 6 correspond to the top boundary. Okay, so what we do, we check this, and if it is equal to 5, then we populate this. Okay, we get the first 2 values, that is the node numbers, and then we keep adding to the bound 1 array, bound nodes 1 array. Okay, and then after we get all the nodes, we flatten the array and we find the init nodes, and these are the degrees of freedom with specified values. Okay, now if we run this code, okay, we already have this for loop for applying the boundary conditions. If we run this code, let's see what happens. Okay, something is wrong. Okay, something is wrong. I'm going to kill this and reopen this. So just bear with me. Okay, so we are looping over this. Okay, so let us comment this. Let's see what happens. Okay, I want to change the path. Okay, nothing happens because we don't have boundary nodes. Okay. Right, okay, so the issue was we didn't have boundary nodes. So we changed it to boundary nodes 1. Okay, so this is the solution. We can Observe this more carefully. Okay, so this is our solution. Now note on the top. Okay, so on the top we have the insulated boundary, so the h equal to 0. Okay, so this is a do nothing boundary. Okay, when h equal to 0, Fe, the element force vector on the boundary element is 0, so we don't need to do anything. Okay, so this is the advantage of the finite element method. Okay, as when compared with finite difference method or finite volume method. Okay, so when for insulated boundaries in the finite element method we do nothing. Okay, so this is our solution. Okay, so next we are going to update this code to include non-zero Neumann boundary condition. That is, for this case on the right hand side when h is equal to -5. Okay, so how to update this code to interpret non-zero boundary condition. That is non-zero Neumann boundary condition. Okay, so I'm going to slowly. Okay, so what do? We have this loop, so where we loop over all the elements, 2D elements, we calculate the elements stiffness matrix force vector, we assemble it, and then we apply the boundary conditions. Okay, so we can add this code either before applying the boundary conditions or after applying the boundary conditions. Okay, so let's do it here. Okay, contribution from Neumann BC. Okay, we have H as -5.0. Okay, and again, we make use of our tags that we have used for the boundaries. Okay, so we loop over the elements, line elements. Okay, so lines. Okay, and what do we want? We want to loop over all those line elements. Okay, so all those line elements for which the tag is 6. Okay, that is, we want to apply the Neumann boundary only on the top boundary. Okay, so for that boundary, our tag that we created from the Gmesh is 6. Okay, so we loop over all the line elements for which the tag is 6. Okay, now, so what do we need to calculate h? We need the basis functions and we need the value. Okay, these basis functions are the basis functions of the two noded element, because we are on the boundary, and the boundary we have two noded elements. So what do we do here? Okay, so to evaluate the Neumann boundary condition, we need to look at each edge separately, and depending upon the coordinates of the edge, okay, we calculate the Jacobian. Note here, so although we are using the 2D element, it is, sorry, we are using the two noded element, it is not a 1D element. So in 2D, this two noded element can be oriented arbitrarily. So this is not a direct to 1D element. We have to make some slight modifications. That modification is dependent on the orientation of that two noded element in 2 dimensions. So the complication is we don't know a priori, that is, we don't know beforehand how the element is going to be. We can only know the coordinates of the two nodes the element is attached to. So here the key difference is the Jacobian. So in 1D element, our Jacobian is dou x by dou z, because we have only x coordinate. But here we also have y coordinate. So what should we take as the Jacobian? Is it still dou x by dou z, or is it dou y by dou z, or something else? Okay. Now, so since we have both, and sometimes for an element, for an edge element that is not oriented along the axis, that is x-axis or y-axis, that is for example this element, both these values are non-zeros. Okay, so in that case, we take the square, like we take the square root of the square of the sum of the square of both values. So this is like a triangle, like diagonal of the like right angle triangle. Okay, again, so to evaluate the element force vector on the two noded element, we use the draw points, and we need the basis functions, the Jacobian from this, and the weights. Okay. So what do? We loop over the elements, and then we get the node numbers. We need to know what are the node numbers of those two nodes are. Okay. So from this we get element number. Okay. We need to get the first two columns, which gives us the node numbers. So then we can extract the nodal coordinates of both nodes. Okay. So for the first node, x coordinate. For the first node, y coordinate. Similarly, for the second node, x coordinate. For the second node, y coordinate. Okay. So now we know the x and y coordinates of both the nodes. Then we can calculate the Jacobian. So here we need dou x by dou xi and dou y by dou xi. And since we are using these basis functions, okay, the derivatives of the basis functions, we know we can calculate them, and our dou x by dou xi simply becomes, okay. So we can calculate this using draw points, which becomes a little bit more complicated. Or for this two node element, we can simplify and use the fact that, okay, so h is constant, okay, so it doesn't change, okay, along the length of the element. And okay, so because of that, so what we can do, we can simplify this. Okay, so what this is our element force vector for the edge element, and we can, once we know the coordinates of the nodes, we can calculate its length. And since h, the Neumann boundary condition, is constant, we can take it outside and we can evaluate this integral exactly, and we get this, okay, as this total as our force vector. Okay, so this becomes simpler when h is, that is the specified Neumann boundary value, is constant. Okay, so once we know the nodal coordinate, what can we do? We can calculate the length of the two nodal element. Okay, square root h2 minus x1 square minus y2 minus y1 square. So that becomes, that gives us the length of the element, and f local equal to, okay, we use this simplified expression. Okay, h a divided by 2 and 2 by 1 matrix. Okay, so 1 1, and then we assemble this. So for this, our node numbers are our degrees of freedom, so we can assemble it like this. So we assemble the local vector into the global vector. Okay, now we need to populate this. Okay, and also add first column, but it shouldn't matter. Okay, so this is how we add the contribution to the right hand side, that is coming from the non-zero Neumann boundary conditions. Okay, now let us run this code. Okay, now you see the value has slightly changed. Okay, if you want to check more carefully, we can do maths of solution. Okay, so maximum value is, okay, let me do this again. Maximum value is 56.849. Now what happens if we make it 0? Fine. Okay, so something is wrong. Okay, let's see if this is actually working or not. Okay, ish. And so okay, we have the boundary sets. No. So are we calculating F lateral? Okay, yes, we are calculating F lateral. Okay, are we assembled correctly? Yes, we are assembled correctly. Right. Okay. Okay, math solution 56.845 with 0. 56.845. Okay, what happens to plus 5? Okay, something is wrong. Okay, just a sec. Right, okay. So the problem is our variable is named wrongly and unfortunately this didn't notify. Okay, so we have -5. Okay, so now the solution has changed. Okay, right. Okay, now with -5 the solution decreases to what we had from when h equal to 0. Okay, when h equal to 0 we had 56 something. With h equal to -5 it decreases, and with h equal to +5 it should increase. Okay, now it is 70 plus. Okay, right. Right, okay. So there was this bug. Okay, now, okay, so this is how we add the contribution from the non-zero Neumann boundary conditions. Here, this is for a simplified case when the value of h is a constant. Okay, but if it is not constant, if it is a function of the coordinate x or y, okay, then what we cannot do it like this. We have to use the draw points. Okay, and for the draw points we have to follow this approach. Okay, so we do this. We at each draw point we calculate the basis functions and then calculate the derivatives, and then the Jacobian, and then loop over, like within the each draw point we add it to the lateral force vector. Right, okay. So with that, we complete this lesson on 2D diffusion. In the next lesson, we are going to look at 2D advection diffusion. If you have any questions, please post on the comment section. Thank you.